is a 3 years project started in 2018. Is a research and innovation project that is grouping together different players around Europe in order to focus on new vision on demand response programs that can be applied with the involvement of prosumers. The coverage is a pan-European project, including Italy, Greece, Romania, Spain, and UK as a player of the project. But there is also the intention to involve relevant stakeholders from the rest of Europe and also international stakeholders in order to gather as much as traction to the project that is aimed at creating a new ecosystem, having a prosumer and partners participating. The partnership, as I said, is composed by complementary partners around Europe with industrial and ICT players, including engineering, Atos, and energy at work. Then we have also stakeholders that are actual player of the energy domain, including Telmi, that is a DSO, also including aggregators like Kiwi operating in UK, and Emotion is a company, Italian company, and also OneESCO that is a servlet. And also as part of a project that is bringing research to the market, we have academy like Teesside University, the CERT Research Center, and the Technological University of Cluj-Napoca that are bringing the innovation from the academia research. And this is the partnership that is coordinated by engineering inside the eDREAM project. The eDREAM project has a specific focus, as I say, that we will see more in depth in the next slide, but main focus is the one of in some way introduce or booster the revolution that is ongoing in the demand response program, with the involvement of customers, in particular of prosumer, and having the collaboration of those prosumer in order to provide services that can be aggregated and offered in the market. In the specific, we have 3 different pilot sites that are experimenting this mechanism. We have a UK pilot site that is managed by Kiwi, when we are experimenting the integration of smart customer and the renewable energy prosumers inside a demand response program. Then we have also the experimentation of some pre-assessment of the prosumer flexibility available in a district that is involving the drone flying over the different areas to identify potential prosumers. And this is performed both in UK and also in the other pilot site that is hosted by CERT in Greece, in Thessaloniki. And the third pilot site is a pilot site in Italy, in Terni area, where ASM Terni, that is the local distributor, is experimenting the flexibility inside the demand response program to manage the grid of the area that they are responsible for. And they are involving the participation of different kind of prosumers, including batteries, also exploited as a second life batteries, are batteries that were used in their first life in electrical vehicles and then are repackaged in order to serve as a storage for the grid, and also involving electrical vehicles that are recharged according to a specific program, and combine the different kind of demand response flexibility in order to offer services for the grid. As I said, the main goal of the eDREAM project is the one to approach the new way distribution networks are going to change the mechanism, are going to revolution the mechanism that are grouping together the different stakeholders. Today, the new role or the increasing role that we are pushing on is the role of the prosumers. The idea is to have those prosumers collaborating among them in order to collaborate further with the grid owner, and having those group of prosumers or coalition of prosumers that can offer added value services for the grid management. Those new customers are customers that we need to understand in which way to involve them inside this new ecosystem that is enabled by the eDREAM platform, the eDREAM technology, and also understanding which way the demand response program can offer new business model, new technologies, services, how to approach a regulatory framework to enable those new demand response. Is a multi-object program that we are approaching in order to identify the overall scenario from different perspective and having one overall approach, that an overarching approach that can actually impact on the context. The main part that we are exploiting is the flexibility market. The flexibility market is quite heterogeneous if we have a look to the different countries in Europe, but also if we have a look in the worldwide scenario. And in some cases, it is still not liquid enough. In some cases, it's still unfair under certain conditions because small players can have not the same chance of big players. So the idea is to group different dimension and different kind of prosumer, but what we need to address is which kind of services are the one that can be provided in this aggregated way, in which way this flexibility can be offered in order to optimize the different flexibility to tackle congestion or voltage balance or grid balancing and so on. And the other one is which kind of mechanism to engage prosumers, engage customers, and keep them inside the ecosystem, because the ecosystem definitely needs the presence of many prosumers in order to create the available offer, the critical mass that can make the services actual service that can impact in the grid. So market-based or incentive-based mechanism, which one to approach, or is it possible to have both of them combined or use it according to the specific case? This is the main goal in a nutshell. This is the group of the goals that eDREAM has. In terms of timeline, the project, as I said, is a 3 years project that is going to be concluded at the end of December. So we already approached the 3rd year of the project. We have already the definition and the architecture specification was already done, and the first round of technology was already delivered with some demonstrators that are running, and you will see some demos of those technologies. Now for this second phase, what we are offering is a tool set, a decision supporting system that is able to help the different roles, different players, actors inside the scenario, and provide those tool set as an integrated, harmonized tool in order to make the specific right decision at the specific right time. And the end of the year, we will have the final release of the platform. This platform will be, as I say, the technology that will be the enabler for the new ecosystem existence and duration and healthy life. This is the big picture of the different tool set that we are going to provide in the platform, and the tool set that you will see in those demo. It's a circle of different phases that encompass the different actions in the ecosystem management. On the left side of the slide, you can see the part of the demos that is more related to the operational aspect of the grid. So the grid operation that is mainly related to DSO needs. And there are some tools that can help the grid operators in order to take their decision, and providing them big data analysis and analysis of flexibility and analysis of kind of prosumers, in which way we can clusterize prosumer, and have some enhanced visualization tools that can offer a very quick view and very effective mechanism to have the summarized information in order to evaluate and approach analysis like what if, or this kind of analysis. This is combined with the two different kind of services provision. I mentioned about the market mechanism to involve the prosumer, and this is the part of the energy marketplace on the top left. That is the part where the marketplace is used to trade energy among the different among the grid owner and the third-party prosumers, or among the prosumers. And on the bottom part, you see the district management. That is more the part of the tool that is approaching the coalition of prosumers. So the approach in this case is to identify one issue, one problem, try to identify the most proper, the most convenient coalition, the most convenient grouping of prosumers that can offer altogether the service to tackle the issue identified. On the right side, we'll see the other part of the tools that is essentially related to the customer scouting, identify new customers to bring inside the ecosystem. And we are using also technologies like drones flying over the area to identify infrastructure, to identify equipment, to identify prosumers. And also the other part is related to estimate which kind of actual flexibility the prosumer can provide to the ecosystem, also in a long-term time frame. The idea is that, for example, PV plant can have some degradation due to the aging of the infrastructure, the aging of the equipment. So there is this kind of estimation in order to have as much as precise evaluation of which kind of flexibility the prosumer can provide and which kind of remuneration it will produce for the prosumer. The pre-assessment is followed by an actual assessment and contractualization of prosumer in order to have the agreement to bring them inside the ecosystem. So this is the big picture. To give you a precise reference, at the start of each presentation, you will see a focus of this big picture with the focus of which kind of tool you are seeing, you are going to see, and which kind of prosumer is involved in this tool, and for which phase of the overall ecosystem life cycle is involved. The more information you will see during this webinar. We have also the website that is essentially the main landing channel we are using for communicating and disseminating with the interested stakeholder and all our partners or our players that are collaborating with us. Then we have some social channels that you can use to follow, or you can refer directly to us for the communication. And this is concluding my introduction of the project, and I'm leaving the scene to the different demos of the actual tools that will show you the mechanism that we put in place. I don't know if there are questions at this stage, or we can go through the tools and we see exactly which are the demos. Madalena?
Yes, we can. I think we can go with the next presentation of the eDREAM questionnaire, and then we'll start the technical part of the webinar. So Giuseppe, if you're ready.
Yes, Madalena. Can you see my screen? Can you see the eDREAM web page?
Yes.
Okay, perfect. Okay. I'm Giuseppe Mastandrea from Manage at Work. I'm the responsible for the activities of Work Package 2, in which we are defining the requirements, the use cases, and the architecture of the eDREAM platform. To this end, from the beginning of the project, we have prepared the questionnaire in order to elicit the stakeholder requirements. The questionnaire is available on our project website, and you can find the questionnaire for external elicitation of stakeholder requirement by clicking on the word questionnaire at the top right of your monitor. Okay. You can start to providing the answers to the questionnaire. Start clicking on begin the questionnaire. Google Forms will appear to this end. This questionnaire was shared from the first phase of the project, as already said, to define the project requirements through a participatory design process, through all the phases of the project, and through the involvement of all the different stakeholders for the project. The gain of better insight into the role, interest, and commitment of each different typology of stakeholders has been considered of crucial importance for understanding where was the starting point for setting common vision and objective for eDREAM projects. Also for this reason, the questionnaire provides a path that allows the stakeholder to answer the question on the basis of their interest, on the basis of their role, for example, to providing the response to the first question and providing the response to the second questions about the knowledge on demand response programs. The feedback coming from the elicitation phase has helped the consortium in defining a specific use cases on the basis of the requirements gathered from this project process. Use cases related to all the functionalities developed in the eDREAM project. And now that the different prototypes are ready for the test and validation, the future responses on this questionnaire will help us to assess the use cases and to validate all the components of eDREAM platform. That's all. I would like to invite all of you to provide feedback on the project by answering this questionnaire after the webinar. Okay, thank you. That's all.
Thank you, Giuseppe. Now I think we can move on the next presentation. Electricity and virtual power plants, modeling and forecasting by Tudor Ciora from Technical University of Cluj-Napoca.
Hello. Hello, my name is Tudor Ciora. I'm professor of computer science at Technical University of Cluj-Napoca, and in this webinar, I will present some of the features implemented for energy forecasting tool, and in the same presentation for virtual power plant construction tool, in which the aggregation of different prosumer will be done targeting the fulfillment of different objectives. First, in relation with the energy in relation to energy forecasting. So our main goal was to try to accurately predict the energy consumption and generation of various prosumers. The overall idea of the approach is to use an assembly-based approach in which different models for prediction were used, different weak learners were used in order to predict the generation and the production of various prosumers, and at the same time to use the assembly to learn the base combination of the outcome of the individual prediction model. In terms of time of the prediction. We have used, we have aimed for short time prediction. Basically, we have used the next 24 hours, so the day ahead prediction. Then during the next day, we have used the intraday prediction, which is basically 4 hours ahead, to further refine the prediction outcome. And then closer to the real time, we have used the 1 hour ahead prediction to leverage on more data in order to generate and to improve the accuracy of the prediction process. Based on the outcome, this information is relevant for the prosumer individually, but also for the other stakeholders, like the aggregator, in case it wants to leverage on its portfolio aggregation. Beside the energy generation and prediction forecasting, we have implemented forecasting of the energy flexibility of various assets. The flexibility was defined as the capacity to increase or decrease the energy consumption in relation to a calculated baseline. Based on this information, we have constructed a tool through which the flexibility for the day ahead could be forecasted. In relation to virtual power plants construction, so we have constructed, based on the data provided by the ASM Terni pilot, a set of prosumers portfolios. So we have various portfolios through which we can look at their consumption. We have forecasted their individual energy flexibility. And then based on this information, we have used nonlinear process optimization to construct the optimal coalition of such prosumers in order to target specific services. So we have constructed the optimal coalition to trade energy. So the main goal is to aggregate a specific amount of energy to be traded, but at the same time to leverage on the forecasted energy price on the energy market to increase and optimize the overall profit of the coalition, of the individual prosumer on the coalition. Then we have constructed virtual power plants with the goal to balance and to improve the reactive power, the power factor of the microgrid by scaling up additional generation. In this case, after deploying the virtual power plant, the power factor is improved. And finally, we have constructed the virtual power plants with the goal of providing or following a desired curve, demand response curve, to be provided for the aggregator. In terms of technology and next steps, our plan is to distribute as much as possible the optimization module and to implement it using fog-based infrastructure, and at the same time, in the final stage of the project, to test an implementation of decentralized virtual power plants construction, leveraging on the blockchain technology and self-enforcing smart contracts. Okay, thank you. If you have any questions.
Thank you, Tudor. I think that we can move to the next presentation, and then we can have a short Q&A session.
Okay.
Okay. So the next presentation is baseline flexibility estimation. Edgar from Teesside University.
My presentation is about the baseline generation tool. My name is Edgar Segovia. This tool was developed for eDREAM project. And this presentation has 4 sections. The first section is about the importance of the baseline. The second section is about input for the tool, processing data, and output. That are the 4 sections. All right, with the first section. And the question is, why are the baseline important? And basically, there are 3 areas that we can, or 3 reasons because we can say that the baseline are important. The first reason is the business opportunities. The baseline open a new business opportunity for energy market or flexibility energy market. The second area is technology impact. Thanks of the baselines, we can develop or integrate new technologies to the grid. For example, the renewable energies. Now, one of the problems with the renewable energies is we cannot match the generation with the consumption. And maybe with the baseline, we can try to match them and we can improve the use of renewable energies. And the last one, but not for that reason less important, is environmental impact. All right, the baseline cannot impact or have not a direct impact of the environment, but thanks of the use of new technologies like storage technology or renewable energies, we can have a positive impact in the environment. All right, now I will go with the second section of the presentation. It's about input for the tool. We'll have 3 inputs: the date, then the tool generates a baseline for that date that the user can select, the historical consumption, and the weather data. The historical consumption and the weather data come in a CSV file format. Here you can see an example of the historical consumption. In any line, there is a date. In that case, in the first line, we can see the year, the month, the day, and then the time and the kilowatt consumption. That is for any half hours step. So there are 48 steps for one day. Now I will go with this next section, the processing data. The processing data used is forecasting algorithms, and all that algorithms are described in the deliverable 3.2 that is already published. And the deliverable 3.6 will be published at the end of the project and going deep with all the algorithms and methodology used for generate the baselines. Methodology used in or studied in that project are comparable day, x of y, recursive and square, additional adjustment, multiplication adjustment, and weather adjustment. All right, now I will go with the last part of the presentation. It's about output. The output come in a CSV format like the input, but this time is generated for one day and also in a step of half hour. So in that case, we can see here 6480, that is the kilowatt consumption for the step as half hour steps for one day. And here you can see one video about how work the tool. Here, for example, the user can introduce the day, then the location for the CSV file, then the user can pick which or can select which methodology you want to use. And at the end, the tool generates the baseline for one day, so 48 predictions for any half hour of consumption. In this project, we develop another tool, this time in Matlab, and this tool can generate baseline for all the buildings. In that case, you can select for all the buildings or for just one, and you can select period of time bigger than 1 day. And in this case, generate baselines with all the methodologies. For that reason, take more time. In that case, you can see the lamp go to red when it's ready. That's take around 15 minutes or half hour, because make the same process, but for any baseline for all the buildings at the same time. In this case, that tool was used for compare the different baselines. And we can see here the different baselines for 2 different buildings in England. Well, at the left for the building number 6 and at the right for the building number 21. In both cases, the first one at the top is the consumption, real consumption, and then we have the different baselines for different methodologies. In this project, we compare that different methodologies, and in order to say which methodology is better than other ones. And in the case of UK, we have here the error for medium error for all the buildings. And we can see in green which are the best options for generate a baseline. In that case are the multiplication and addition adjustment for X of Y high and middle baseline. We can see here in September, for example, we have the error that 12%, and here for October we have an error of 6%. So if we keep we select one of these methodologies, we can say that the error will be lower than with other methodologies. In the case of Italy, we have big data, so we compare different years. In that case, 2016, 17, and 18. In the multiplication error and additional X of Y, the better one. Have that like better methodology was not. In that case, it's
Edgar, I can't hear you. I think it isn't just me.
You can
with a lot of interruptions.
I'm sorry.
It got disappeared for a bit. The image works, it's just that the audio just...
Yes.
Can you hear me now? Oh?
Yes, but you're breaking up a bit.
Okay. More or less when you see the videos?
Yes, we could see a screen, but the audio wasn't very clear for the last 2-3 slides, I think.
All right.
From slide 17, probably.
That was. Explain the different baselines graphs.
Yes, I think this was okay, but last one, 17 slide.
All right. Well, this one. Thank you for. Okay. For that table is for the Italian case, and in that cases we have the information for 3 years. So we compare different years, and we calculate the error for all the buildings during this period of time. And we can see that the multiplication adjustment and the additional adjustment with 20, 35, and 35%. And in that case, the minimum error was in 9, 8, and 6 buildings. So if we select one of that methodologies, we can say that the error will be lower than with other methodologies. In that case, it's important to say that the worst methodology was a normal simple regression, and maybe it's not a good idea to use it. And thank you. I'm sorry for the problem with the audio.
Thank you, Edgar. Now we can have a short Q&A session. If you have any questions or feedback, please share it with us. You can use either your microphone or the chat section that is in the right corner on top of your window. So if there aren't questions right now, I think that we can move forward to the next section with multi-building demand response characterization through thermal, optical, and LiDAR information fusion. And we'll have the first presentation, aerial survey techniques using visual, thermal, and laser imaging in UK.
Madalena, before to start, there is one question in the chat.
Okay, sorry, I haven't seen that. Okay, hi, thanks for the presentation. I wonder, how did you segment building loads? If one of my colleagues could answer the question.
Edgar or Tudor?
Edgar, yes.
I don't know. I'm not sure what does he mean by segmenting the building loads. In general, when it comes to forecasting, we have used machine learning based algorithms. In this case, we have trained the machine learning algorithms based on historical data, and we have used then the trained model to generate forecasting for the day ahead. In case of the baseline is a little bit different. For the baseline, we did not use forecasting algorithms or short-term forecasting algorithms per se, because it needs to be tracked both by the I would say both by the aggregator or the DSO and the prosumer. So in this case, the methods are based on I would say average-based methods. So I don't know. The average of the last 7 days, the average of the most relevant days in the last 30 days, and so on. Regarding the second question on the energy marketplaces that we are targeting, basically we are targeting two types of energy markets. So we are targeting the energy market. So in this case, we will see later in this webinar the implementation of a peer-to-peer energy market that goes into the direction of empowering prosumers to trade energy in the peer-to-peer fashion. And the second type of energy markets are the flexibility markets. and also in this case, our idea is to go into a, I would say, decentralized fashion in empowering prosumers to aggregate on the fly their flexibility and trading it into such a market.
Thank you, Tudor, for your intervention. Okay, so I think that we can move on to the next presentation of aerial survey techniques. Charalampos Saros from Teesside University. You can begin.
Hi, a bit of a forward first. Hi, this is Charalampos from Teesside University. What I'll be showing is a short technical demo of showcasing the various techniques we use for aerial survey, methods for demand response, potential calculation. This will be run in a 360 kind of way. It's a bit of a strange method. It will run on an iPad, and then I shall be just streaming this to your screen. So in short, before I move on to the streaming of the iPad, what we do is we take our equipment to the potential site, and then we take scans using both the visual, the thermal, and the thermal elements of cameras, and also do laser scanning using LiDAR. And then we do energy performance simulation and demand response estimation based on the data we collect. I shall switch to from my camera to my screen of the iPad. Can you see on the screen saying aerial survey demo at the moment?
Yes, Charalampos.
Right, okay, then I can just hit the play button. So we have two test sites, one in London at Greenwich, provided by our partners QE Power, and one at Greece, provided by CERT at Thessaloniki. I have some footage from one of the test scans we've done in London. You can see here a drone taking off from a position at the Ernest Dents estate. Starting its mission, going to the edge of the roof of that building, then carrying on with its mission, flying until the end of that building, and then completing its mission by just returning back to its takeoff point. When I move my iPad left and right, we can just see different sections of the video, because we shall be including more data, as you'll be seeing in a bit. So what we captured during that scan, we had both visual and thermal bits. This is the visual part of the video, the data we captured, and then on the side is the thermal part, so we can just look at any place, whatever we want. The numbers on the bottom represent thermal values of every single pixel on the thermal imaging footage. What we also have done was laser scanning of the area using a 16 laser beam LiDAR scanner. So you can see every dot on the image provides us with those data over here, which is X, Y, Z, several timing values and other data that we use in order to have more accurate measurements and provide us with a model. So at any time we can just look at the left, that's the actual laser imaging part, or to the right in order to just check the data. So we did further tests and further scans in one of our other partner sites at the Smart Home at CERT at Thessaloniki in Greece. So the drone again is flying from one side of the building and then capturing visual and also the thermal data. On the top, you can actually see some PV arrays really glowing. And then on the bottom, all of them are thermal values in Celsius, being for every single pixel of the thermal footage. What we also done during those scans was create models based on photogrammetry techniques. So this is one of the models created from the smart home at Thessaloniki. And what we also have done was, based on those pictures, we created, let me just switch to 3D mode. This is the resulting geometry of the building. And this is the final result. So we can just observe. And you can see the several assets in the building, and the presentation right after mine will go into more detail on how techniques are used to automatically detect certain assets. For example, here you can see PV arrays. On the corner, there's a photothermal boiler. On this side, there's some HVAC units for air conditioning, and then some more PV arrays over here. What we also have done was we experimented with more techniques in order to be able to observe this model in both virtual and augmented reality. So right now, for a moment, we'll just switch to the iPad's camera in order to find the plane. Excuse the mess of this place. So, trying to find a flat surface. Sure, here it's just about fine. So what I'm doing now is physically walking around the building. And if I want to see a specific part, I can just go close to it and then see those arrays, for example, or the photothermal. I can go around it and then check what's going on there for the HVAC units. It's also a useful tool for checking for several malfunctions or any other maintenance tasks. For example, if any of those arrays was malfunctioning, you would see a distinctly different color on it. And that pretty much concludes the presentation for the aerial survey toolkit from our side. So if you have any questions, you can ask now, or is it the end of the section? Whichever. Thank you.
Thank you. Okay, so we have one more presentation from this section from Pascalis Gaidatsis from CERT, Thessaloniki. The presentation is about a deep neural network-based method for the detection and accurate thermography statistics estimation of aerial surveyed structures in Greece. So Pascalis, if you're here, you can start the presentation. I can see Pascalis on the list, but I don't know if he can hear us. Okay, so he is on.
Yeah, I believe the sound is working because we just heard sound coming from his user.
Yes. Okay, great. Okay, I think that he's writing. No. No, we can't.
Okay, Madalena, in that case, if Pascalis don't solve the problem, I think that we can move to the next presentation if there are not any questions by the participants.
Okay.
And postpone the presentation of Pascalis when the problem with the micro will be solved.
Okay, great. So we can move to the next section of our webinar, Next Generation Demand Response Services for Aggregators and Customers. And the presentation will be held by Fatih Abuhem from Teesside University.
Hello, this is Pascalis. Can you hear me?
Oh, hi, Pascalis.
Ah, okay. I finally caught you. Okay. Let's proceed and I will continue later if that's no problem.
No, at this point, I think that we can proceed as by the...
No, with Pascalis. Conclude the part of the drawing, yeah. Pascalis, please carry on.
Yeah, yes, I agree with you, Mincha.
Yes.
Okay.
Sorry for the technical mishap. The microphone seemed to not be working. Okay, moving to share screen. So in this presentation, we're going to see. Can you see my screen?
Yes.
Perfect. So taking the input from Matt Haralabos has previously shown you. The input from the image processing pipeline consists of two shots taken from optical and infrared cameras mounted on a Matrix M200 UAV. Note that the two cameras have a slightly different field of view, as well as different intrinsic and extrinsic parameters. Semantic pixel-wise cues were extracted by using a deep learning technique called feature extraction. This involves the use of a state-of-the-art pre-trained neural network, and in this visualization, deep features seen in the right image are juxtaposed on the corresponding optical video frame on the left, and similar colors denote semantically similar content. Following, an unsupervised learning technique is then applied on deep features, that is PCA and K-means, in order to cluster each frame semantically coherent entities. So in this manner, the main structure, the smart home, is identified and is the estimated mask shown in this frame here. The detected mask is then used to select only the relevant thermal intensity values left. When computing thermal intensity statistics, note that this does not make a significant difference, and this allows us to compute accurate temperature statistics on the structure of interest. Therefore, further processing on the detected mask and the optical camera input leads to detection of the PV element assets that are situated on the building's rooftop. You can see here. The full processing pipeline was written in Python using TensorFlow and NumPy and SciPy, if I am pronouncing them correctly. And the video was made using a UAV at the service facilities. So that's all from our side. Thank you, everyone.
Thank you, Pascalis. Now we can have a short Q&A session. If you have some questions or want to provide us with some feedback.
Okay, Madalina, it seems that there are no questions in the chat. This is concluded the first part of the demos that are related to what I mentioned as the pre-assessment, the drones flying and the image processing in order to identify equipment of the different potential prosumers that can offer flexibility. So this is the first step before to engage the new prosumers and bring them in the ecosystem. Okay, Madalina, I think we can carry on with the next presentation, next demo.
Yes. So the next presentation is will be done by Fatia Buhem from Teesside University. Decision-making and demand response services optimization toolset and PV-RES degradation and trend analysis.
Okay, can you see my screen?
Yes.
Okay. So if you can't hear my voice, please let me know.
Okay.
Hello everyone and welcome to this webinar. My name is Fatia Buhem, Research Associate at Teesside University. In this webinar, I'm going to present the decision-making and DR optimization toolset developed by Teesside University within the eDREAM project activities. The decision-making and DR optimization toolset is one of the core components of the eDREAM platform, and it exists within the district management tools. The main functionality of the decision-making and DR optimization toolset is to provide the aggregators and energy retailers with toolset that enables them to utilize their energy resources in an optimal way. In recent years, the transforming of traditional power systems from centralized electrical power generation plants operated by large utilities toward clusters of distributed generation networks has received a great deal of attention by the power providers over the globe. These distributed generation networks are termed as virtual power plants. Virtual power plant is defined as a network of decentralized medium-scale energy generation units treated like one single power plant. The units aggregated on the virtual power plant can be wind turbines, solar systems, and combined heat and power units, as well as flexibility offered by prosumers participating on the DR programs. The toolset consists of two main models, decision-making model and virtual power plant optimization engine. The decision-making model provides the virtual power plant managers with the optimal amount of the power reserve that is needed to balance the fluctuation comes from the renewable energy resources and the flexibility provided by the DR programs. Once the power reserve has been calculated, the virtual power plant optimization engine will provide the virtual power plant managers with the optimal dispatchable schedule of the generation units participating on the virtual power plant. The output of the engine will be the optimal list of generation units which should be used and the set points of its selected units, which satisfies the power demand and the power reserve. The general structure of the toolset is as shown in this figure. The tool uses the output from other components of eDREAM platform. These components are prosumers consumption production forecast, prosumers flexibility forecast, prosumers baseline estimations, and historical data related to the prosumers from database, as well as dispatchable generator data, which is also from the database. These data are used by the tool to first estimate the uncertainty of the PV generation forecasts and the uncertainty of the flexibility estimation, then make decision for the reserve and do the optimization. The output of the tool will be optimal scheduling of the dispatchable generators, aggregated virtual power plant BV power generation forecast, and aggregated virtual power plant flexibility estimations. For the uncertainty of the BV generation forecasts, the forecasts obtained from the production forecast component are deterministic, which means only a single value in each target hour is provided. Thus, the tool, and based on the historical BV generation data and past forecast data, calculates the forecast error and estimates the prediction intervals. For the uncertainty of the flexibility estimation, the upper and lower bounds of the flexibility of each prosumer are obtained from the flexibility estimation component. Using these limits and the baseline estimation, the tool estimates the flexibility of the VPP and its prediction intervals. Based on the uncertainty analysis of BV generation forecast and flexibility estimation and the risk index selected by the operator, the decision-making module will calculate the power reserve, which then used by the optimization. The idea of the optimization is that the optimization algorithm will select the optimal set of generators which generate the required demand, and also able to ramp up and down to balance the variations of the BV generations and flexibility provided by DR programs. The optimization problem is formulated as a customized unit commitment and economic load dispatch problem, and the objective is to minimize the fuel cost, where in unit commitment optimization, the operation schedule of the dispatchable generator is evaluated, which means identifying which generation unit will be on and which will be off. Then in economic load dispatch optimization, the set points of these units are calculated. As the independent variables of unit commitment are discrete and the independent variables of the economic load dispatch problem are continuous, and algorithms which can deal with both kinds of variables is needed. Or we might use two different algorithms, one to solve unit commitment and another one to solve economic load dispatch problem. To solve the optimization problem, a series of optimization mechanisms based on GenOpt optimization program and the method of Lagrange multipliers and priority lists were developed. GenOpt is a generic optimization program developed by Lawrence Berkeley National Laboratory, University of California. GenOpt has a library of various optimization algorithms such as generalized pattern search, particle swarm optimization, hybrid global optimization. However, not all algorithms of the GenOpt program are able to solve problems include both discrete and continuous variables. For this reason, and to use the full capability of the GenOpt, another two optimization methods has been implemented. Lagrange multipliers, which is used to solve the economic load dispatch problem, and used with the GenOpt algorithms which can solve problems with discrete variables. The other method is the priority list, which is used to solve the unit cost problem, and used with the GenOpt algorithms which can solve problems with continuous variables. A user interface works as a supervisory program that controls the operation of the optimization engine was developed. The interface also provides a user-friendly environment to use the GenOpt program, which is not present with the current versions of the GenOpt software. One of the main objectives of the user interface is to create an algorithm selection framework that acts as a decision support system to help the operators to take the most advantage of the GenOpt program. In the remaining time of the presentation, I'm going to run a quick demonstration of the toolset. We start the optimization by selecting the method. We have three options to choose, either GenOpt, priority list GenOpt, or GenOpt Lagrangian method. If we choose GenOpt to solve the optimization problem, this means that the GenOpt will be used to solve both unit commitment and economic load dispatch problems. In this case, only the algorithms which is able to solve problems with mixed, discrete, and continuous independent variables will be enabled. If we change the selection to priority list GenOpt method, then only the algorithms which is able to solve problems with continuous independent variables will be enabled. Once the optimization algorithm is selected, its configuration and settings will be uploaded. These settings can be easily amended and changed by the user. After selecting the method and the optimization algorithm, we need to upload the data. 5 files need to be uploaded. Generators data, loss coefficient of these generators, demand curve, flexibility estimation of the prosumers participating on this VPP, BFE forecast data, and historical BFE production data. To start the optimization, we press the Start Optimization button. The general program will start. It will generate the independent variables, send it to the model, and reads the value of the objective function. Once this completed, the cost point of each generator at each time slot will be displayed. The output of the optimization engine is shown in this screen. On each time slot, the power demand, the minimum cost achieved by this algorithm, and the set points of the generators are shown. The results also are presented graphically on the user interface. At each time slot, the set points of each generator and the cost are presented. And that is the end of the presentation of the decision-making and DR optimization toolset. I have presented its objectives, structure, and demonstrated its functionality. Thank you for listening. So I will start with the second presentation.
Okay.
This second presentation is actually covering the part related to the PV degradation. So it's part of the pre-assessment phases, because the one that you just saw is a presentation for the decision supporting system for the different stakeholders, and the next one that Fatih is going to present is the presentation of the tool for the calculation of PV degradation in order to estimate the actual production of flexibility in a long-term period.
Okay, so let us start. Now I'm going to present the degradation rate and trend analysis component. The presentation is divided in two parts. In the first part, I'm going to provide some background and description. And in the second part, I'm going to demonstrate the use of the component. The term degradation rate is defined as the maximum rate of reduction at which BFE lose their performance over the time. If we can calculate the degradation rate, we will be able to accurately estimate long-term forecast of the BFE production. Although most of the BFE manufacturers guarantee that at the end of 25 years of operation, a maximum of 20% reduction can be observed. They also reported that a maximum of 1% is expected for the first 10 years. The study showed that this assumption is not always true, as the performance of the BFE depends also on the environment and climate type, and can be much more than the predicted values. Different methods has been proposed to estimate the degradation rate. These methods can be classified into two categories: indoor-based and field-based. In indoor-based, the BFE needs to be transported to the testing facility, which is time-consuming and imposes the risk of failure due to mishandling. On the other hand, the field-based requires long-term monitoring. Between 3 to 5 years data is required to obtain accurate estimation. Also, methods to reduce the impact of the outliers is needed. When a field-based method is used, a statistical technique is required to calculate the degradation rate. Perhaps the most used one in the literature is the linear regression. However, this method is very sensitive to outliers. For this reason, we have implemented a classical seasonal decomposition method, which is considered much robust to the outliers than line regression. The main concept of the classical seasonal decomposition method is that the long-term trend of the BFE performance data series consists of three components: trend, seasonality, and residual. And the idea is to isolate the seasonality from the time series and apply a linear regression on the deseasonalized data to obtain the DR. To reduce the impact of the outliers, a filter based on the average and standard deviation of all similar months was used. The data points which exceeds or fall below specific limits are identified as outliers. These points are replaced by estimated values calculated based on the power generation of the PV at the same time period of the other years. Two metrics are calculated by the component and used by the operator to evaluate the results obtained from the component: the statistical uncertainty of the regression line and the mean absolute percentage error. The component has been tested in 4 years dataset received from Kiwi, the UK pilot site of the eDREAM project. The calculation of one of these sites is presented on this slide. The blue line represents the measured data, and the orange represents the forecasts. The line regression is presented in red line, which is used to calculate the degradation rate. According to the component, the degradation rate of this system was 1.3%. Now, I'm going to run a video that demonstrates the use of the component. We start the calculation by uploading the data. Let us go to the Kiwi data, site A. We can select prosumers. If there is more than one prosumer in data file, so they will be listed here. So we have just one prosumer in this file. Then select the method. We have implemented two methods. The first one is multiplicative decomposition, and the other one is additive decomposition. So let us go for additive. Then we select how many years we would like to forecast. Select the SD filter. Keep the constant as it is, 1. Then we calculate the degradation. The data related to calculation are presented here in this window. We can see that the degradation is 1.3, the uncertainty is 0.0088, MAB is 15.1, yearly MAB is 2.6. In upper window, we can see the blue line presents the measured data, green line presents the trend extracted from it, and yellow line presents the regression line, which is used to estimate the degradation rate. In the bottom window here, we see the blue line presents the measured data, whereas the green line presents the data after filtering. We can see here that the filter has identified this as outlier, so to replace it with some other values. The yellow line presents the forecasts. If you would like to see the forecast for the next 12 years, so just press this button. So this is what we expect to have within the next 12 years. We might change the view to yearly. So this is the production 2019, and this is in 2013. So we can see that there is a drop expected on the generation of this system. That is the end of the presentation. Thank you for listening. Yeah, so thank you. If there's any questions.
Thank you. Thank you, Fatih. I think that we can move to the next presentation, Big Data Clustering Techniques for Load Profiling and Customer Segmentation by Lourdes Gaello from Atos.
Hello, good morning, Madalena. Well, this module is actually a set of three tools: load profiling, big data clustering at multiple scale, and customer segmentation included in the grid operation group, which enable energy services providers like DSOs, aggregators, or VPP managers to segment customers in clusters according to different objectives. Also, the module is able to recognize patterns, profiles of new potential customers and assign them to the proper cluster. Thanks to input received from the pilot site and baseline flexibility estimation module, the functionalities of this module are expected to support energy services provider in decision making. The module is based on big data techniques presented in the video with details on the programming, data flow, and the interconnection. The video has been edited with text description, so you will be able to see the presentation and read by yourselves all the detail with no voiceover description.
Okay, thank you, Lourdes. Would you like to add something to your presentation? If not, then we can move to the next presentation. Interactive visualization platform based on graph analytics. Again, Pascal is from CERT.
Yes. Can you hear me this time again?
Yes.
Yes, thank you. Okay. So moving on, here we have the visualization platform. Please tell me when you can see my screen. Can you see my screen?
Yes.
Yes, perfect. So at the part of the video, we're going to see three aspects. At the first one, we're going to see the user preparing the prosumer, more specifically preparing for a DR event. On the second section, we can see the aggregator monitoring its PODR portfolio. And here we can see him selecting various prosumers and compare them with one another, and with the mean, max, and average value of the DR portfolio. The KPIs in the caveat diagram are the CO2 reduction, the energy consumption, and the demand flexibility of each of the users. Selected. And this is for a specific date and time. He can also use another aspect of the project in order to compare the user's portfolio regarding energy consumption and energy generation in this particular view. And in the middle of the screen, you can see the merged, that is the energy consumption minus the energy generation. And here you can see that hovering over in one of the diagrams, he can highlight the users in the others, therefore having a more complete view. And he can also switch to demand flexibility or CO2 reductions. That is the other KPIs used in this view. And here we have the DR aerial survey management, that is the aggregator, is able to have a quick overview of the areas surveyed and the buildings inside those areas, which we have seen in previous videos of this presentation. And here we can see that by clicking the user, he can zoom into the area and the buildings that have been surveyed and see some details about those buildings. For example, the energy class, or even the assets of those buildings. That is the PV panels, the HVAC, or the solar water heater that have been identified from the methods that we have presented earlier in this presentation. This includes existing customers of the DR portfolio and also new ones that are going to be registered promptly. That's all from our side.
Thank you, Pascalis. So with this presentation, we have concluded the third section with the next generation demand response services for aggregators and customers. If you have any questions. Okay, if not, we can move to the last section. We have here a presentation by Tudor from Technical University of Cluj-Napoca regarding blockchain-driven demand response and flexibility management and secured blockchain-driven energy market.
Okay, so the first presentation is regarding the decentralized control of flexibility. In this case, we have created a tool based on blockchain and smart contract that allows the DSO aggregator and prosumer to control in a peer-to-peer fashion the distribution of flexibility. So the main actors interacting with this tool will be the DSO, the aggregator, and which is willing to control its portfolio of prosumers, and the individual prosumers that are enrolled in such a program. So taking this one by one, first the distribution system operator. he log into this application, he can see the status of a specific microgrid. Based on the status of the microgrid, we can see, for example, in this scenario that we have created, that there is a forecasted energy production which is higher than the estimated consumption for the next day. In this case, the DSO will be able to create a flexibility request, which basically will aim for an increase of energy consumption to meet the overall generation in that specific microgrid. Next, we can see that based on his flexibility request, there are two aggregators that are activated and are willing to deal with that request and deliver the estimated amount of flexibility. Then, based on the estimated amount of flexibility to be delivered, the aggregator will, the DSO will select a specific aggregator to deliver the flexibility in terms of increased consumption. Now, from the aggregator perspective, the aggregator logs into its profile. He can check its portfolio of prosumers. Based on the flexibility request created by the DSO is directly injected into the smart contract managing the behavior of this aggregator. That smart contract will aim at managing the portfolio of prosumers. Basically, in this case, what we're trying to do, it will try to identify a subset of prosumer that can be aggregated and deliver the expected amount of flexibility. Here we can see how the smart contract is actually working. We can see the flexibility request of the DSO, and we can see the portfolio of prosumers selected to deliver the specific amount of flexibility. We can see the estimated profile of each individual prosumer. What is important to note is that using blockchain and smart contracts, these estimated profiles can be and are directly injected into the smart contracts, managing each individual prosumer behavior. So then the prosumer will be able to know in advance the estimated goals that it need to deliver in the next day. Then, during delivery time, one of the technology is the fact that the settlement of imbalancement can be done in a real-time fashion. In this case, we have managed to bring the settlement of imbalancement, leveraging on the distributed ledger technologies close at a half an hour time period. We can see here the monitored energy consumption and production in real time for each individual prosumers, and we can see the potential deviations that are registered by each individual prosumers in terms of not delivering the expected consumption levels. If we log as a prosumer, so the prosumer can check its estimated flexibility. So this is the flexibility for the next day using the forecasting tools that I have shown in my first presentation. He can check the baseline, which is calculated, the flexibility above and flexibility below, the requested flexibility, which the prosumer receives from the aggregator. This flexibility is in the range between, in this case, between the baseline and flexibility above. This flexibility request is automatically injected into its smart contract. So the smart contract that regulates its energy consumption, the prosumer energy consumption behavior. And here we can see the monitored energy consumption as is as it's being delivered by the power meter. Each time the consumption is registered from the power meter, that consumption is registered as a transaction in the blockchain. It is compared automatically with the requested flexibility, and if relevant deviations are being registered, in this case we have considered a specific threshold of 10%, that prosumers could be penalized. Otherwise, the prosumer is being rewarded. So at the same time, we are conducting not only a settlement of energy, potential energy imbalancement, but also we can deal with the financial settlement of flexibility delivery, and based on how well it follows the curve, the prosumer wallet will receive tokens. So this is the first presentation. Was on flexibility management. The second presentation is regarding the peer-to-peer energy market. The main goal of this market is to allow any prosumer to trade energy in a peer-to-peer fashion. In this case, we have two roles for this market. Basically, we have a market operator, and we have the prosumer. So every energy player could act as a prosumer and can buy and sell energy in this specific market. All the processes are being automatized using smart contracts. So in this case, the managing of the market session as well as the regulation of the bids and offers are being done in automatic manner using smart contracts. In this case, the market operator could check the profiles for the next day, who can check the bids and offers placed in the current market session for the day ahead. He can look to see energy trades that have been resulted. The smart contract managing the market session is able to match the bids and offers in a peer-to-peer fashion. And at the same time, it is willing to identify the settlement price. Based on the registered bids and offers, transactions are being generated, and thus this transaction can be shown here. The transactions are registered on the chain, and during the actual delivery, these transactions, the promised delivery and promised consumption are actually monitored based on the data coming from the smart meters, and this information is then used to actually settle the registered transactions. So for financial validation of the transaction during delivery. If we log as a prosumer, so as a prosumer, I can check my information. I can see my forecasted consumption, forecasted production. If I have production, I can see the previous session reference energy prices. I can place bids and offers, so I can buy and sell energy. Based on this information, the registered bids and offers are registered on the chain as transactions. After that, the bids and offer are matched, and the transactions are mined. We can see here blockchain details about how the transactions are being registered. And during the actual moment of the delivery, the monitor data from the smart meters are registered on chain, are automatically compared by using the self-enforced smart contract with the promised value set in bids, set by the bids and by the offers, and based on this, the actual distribution of tokens in the wallets associated with the in the prosumers is being set. Okay, so this concludes my presentation. If you have any questions.
Okay, thank you, Tudor.
Thank you.
So this was the last presentation of our webinar. Now we can have a Q&A session and a final discussion.
Sorry, Madalena, if Tudor can stop the sharing of the screen. Yes, thank you.
Okay, so now we can have a final discussion. Vincenzo, if you would like to add something?
Yeah, as a final closure of this presentation, I would like to remark that different tools were shown because the approach that we intend to propose as an enabling technology for the eDREAM ecosystem is the toolset approach. So the idea is having different tools that can offer different kind of support to the different stakeholders that are part of the ecosystem. The ranging of the support is including definitely operational aspects related to the grid management and operational aspects related to the prosumers coalition and marketplace, but also the part of feeding the ecosystem with new prosumers and keeping because our idea is that the ecosystem is definitely requiring to have enough number of prosumers collaborating all together. Otherwise, the risk is that the services cannot be performed in proper way because the aggregating services it's optimized when the offer is wide and we have a different combination to examine and in order to detect which is the optimal or the proper one. Okay, then I think it's time to the attendees to put questions if you have questions or if you want to remark or retouch some points of the tools. Okay, Madalena, I think if there are no questions, you can provide back the reference to the project in order to give all to the attendees the reference for in-depth knowledge on the project. I would to take this chance to thanks from my side and thanks from the partnership for the time that you spent in this webinar. This is one of our wide efforts to disseminate the knowledge on the project and try to spread as much as possible the information about our project, and I will kindly invite you to stay in touch with us.
Okay, thank you, Vincenzo.
Okay. Thank you so much.
Thank you, everyone. We appreciate your participation. The webinar registration will be available on eDREAM website, but I will also send it to you on email. So this is our website. Here you can stay in touch with us and find more and see how our work is progressing. Okay.
Okay, so thank you everybody again.
Thank you. Have a nice day.
Giuseppe, maybe you will remember.
One message for all the participants, all the attendees. Don't forget to answer to the questionnaire to provide the feedback for our project that will be useful for the last phase of the project about the validation of our platform. Okay, many thanks.